gymnastics announcement to be heard. So, really briefly.
Hi everyone, I'm Katie, and the women's gymnastics team is hosting our ECAC Conference Championships tomorrow at 12 in Catherine. And it would be really awesome if everyone came because this only happens every 6 years, so it won't happen again while we're here. And it's free with a student ID. And the men's team has a senior meet on Sunday at 1, so if you want to come out too.
Nice. Yeah. All right, let's talk business for a sec. So, the exam is when? 2 Mondays from now, Monday after Easter. That's about 10 days. Okay, so hopefully everyone got the office hour workshop schedule. I'll update that once we get through exam 2, but that covers up until that point. And so office hours yesterday were really good. They were up in the conference room. There were like 7 or 8 people there, and it was pretty informal. And so it's a good place that you can still get some one-on-one and have your questions answered, and not be in around 60 people at a workshop or something. So if you can make those, I recommend you do so. All right, so we have another office hour today from 12:30 to 1:30, and then I will be skipping campus. I've got a flight to catch in Richmond, and so I won't be available after 1:30 today. And I'm also not getting in until Sunday evening on my return flight. And so is there going to be a workshop on Sunday? No workshop on Sunday. So otherwise, from Sunday on until the exam, I think you have a chance to come see me every day except Saturday. So lots of opportunity for help. All right, that's all I got right now. I'm a little bit emotional today. I've got to board Sadie, and you can tell a child that you'll be back. But Sadie spent her first year basically as a shelter dog in a kennel, right? And so I've got to take her into a kennel and shut the door and leave her for like 2 full days. And hopefully she'll be fine. There's supposed to be other dogs there, and she'll be distracted, but I'm not sure I will be. So hopefully she'll be okay. All right, so let's finish up our carbocation mechanisms. Oh, and one more thing. The homework, there is homework due tonight, right? It's been due for a month, and like I said, I'll be traveling the rest of the day. So if you need help on the homework from me today, I love you guys, but it's not probably going to happen. So hopefully you've gotten started, and you've got plenty of people have been asking me questions over the last couple of weeks for it. So hopefully you've had your questions answered. Okay. So we were talking about 1,2 hydride shifts last class, and I said there was another possibility you have 1,2 alkyl shifts. And so we went ahead and made sure we understood what an alkyl group is. And so an alkyl group is any group of carbons and hydrogens together. So a methyl group, an ethyl group, propyl, tert-butyl, isobutyl, sec-butyl, sec-propyl, or there's not a sec-propyl, there's a sec-pentyl. All right, anyway, you don't care. The point is, any collection of C's and H's is going to be an alkyl group. And so in cases where we can't have a hydride shift, what we can actually see is the shift of an alkyl group. And so in this case, what we've got is we've got an alkene, and we're going to hit it with HCl. So we hit it with a strong acid. What's the first step always going to be? Protonation. And so what we do in this case is we're going to protonate. And furthermore, we're going to protonate the secondary carbon or the primary carbon. Well, which one by protonating would form the more stable carbocation? Yeah, if we protonate the primary carbon, we're going to protonate here, and then we'll end up electron there, which is always going to be better than a primary carbon. And so we might ask ourselves, well, that still doesn't make a lot of sense. How can we get from basically this starting material to this product? And so if we look nearby, we see we've got 3 methyl groups off of this carbon, right? So we've got 1, 2, 3. And so what do you think is going to happen? We're going to undergo a 1, 2 alkyl shift, right? All right, so one of our methyl groups is basically going to migrate over to that carbocation. Okay, so if we draw the electron, or if we draw an arrow pushing picture of this, where do we start our arrow? Electrons, always electrons. So we'll start them at this sigma bond, and we draw them to the carbocation, just like that. All right, so what we've got here is we've got carbon number 1, and so carbon number 2 nearby is a carbocation, and so by undergoing this 1,2 alkyl shift, we're going to form a new carbocation, right? So we're leaving this carbon electron deficient because this alkyl group is standing up and walking away with its electrons. And so our next intermediate would be a carbocation that looks like this. All right, so now this carbocation is what kind of carbocation? Yeah, this is a tertiary carbocation. So we've gone from a secondary carbocation to a tertiary carbocation. And so do we have a good reason for this to occur? Yeah, absolutely. We can form a more stable carbocation by undergoing this 1,2 alkyl shift. And so what we end up in this case is now a tertiary carbocation. And so now we can basically snap together our chloride with our carbocation. And so in doing so, we end up with that product that I've shown. All right, so basically, it's always going to be more favorable to do a hydride shift than an alkyl shift. So if you can do a hydride shift, do it. And only in cases where you can't would you consider an alkyl shift. So hydride shift, more favorable than alkyl shift. All right, so I think I'm comfortable calling it good there. All right, so that's going to close our Roman numeral. So on an exam, I understand that now we've learned the carbocation mechanisms. They do have Markovnikov regioselectivity, but they have very poor stereoselectivity, which can result in a lot of different products. And furthermore, because of these shifts, we can form even more products. It's not unheard of to do a reaction and end up with like 10 or 12 different products. Is there ever going to be a case where on an exam I say, hey, draw the 10 or 12 products that could occur from this? No, and in fact, I'm going to most likely, you'll see reactions or questions written one of two ways. So I might even say predict the product, ignoring any possible shifts. I just say ignore any shifts. They can occur, but we don't care about them right now. Just show me the product. Or what I could do is ask you to maybe draw a mechanism that looks like this, where you see a starting material, you see a product, and so it doesn't make sense for this product to come from this starting material without a shift. So basically, I'm going to be trying to guide you in cases where there will be a shift or where there won't be a shift. So your ability to recognize just out of the blue when a shift will occur isn't as important as just knowing that it can occur and that it can help us form different products. Okay. So that closes Roman numeral 3, I think. Is that right? That's what I've got. So Roman numeral 4, we've talked about carbocation mechanisms, and so now we're just going to talk about some reactions. So Roman numeral 4 is going to basically be C plus reactions. Okay, so essentially this is going to be a little bit of a review because we've been using a lot of these reactions thus far. So when we talk about carbocation mechanisms, the regioselectivity we can describe as what? Guy's name starts with an M. Markovnikov. What we want to do with C plus mechanisms is we'll say, well, it's going to follow Markovnikov addition, and it's going to give us the Markovnikov product because that's the product that's going to go through the more stable carbocation. So for regioselectivity, we would call it Markovnikov. What about stereoselectivity? Does a carbocation mechanism have any stereoselectivity? Well, we've seen in both steps, we start out with the protonation of a double bond, and of course a double bond is planar, and so that protonation can happen on the top face or the bottom face, so there's no selectivity there. And then the second step is going to be where we snap our nucleophile to our carbocation, and again, a carbocation is going to be planar. We can approach from the top or from the bottom, and so unfortunately what makes these carbocation mechanisms so complex is the fact that there is no stereoselectivity, and so in this case, we would say there is none. But it's pretty much just the carbocations that don't show any stereoselectivity. And so the number of products that we can make will shrink, basically, as we go forward in the next few lectures. All right, so furthermore, we'd just like to quickly add that carbocation rearrangements, so that's our 1-2 shifts, only occur with C plus mechanisms. And that should make a little bit of sense because none of the other mechanisms we talk about go through carbocation. So it's a prerequisite to have a carbocation to go through a 1,2 hydride or a 1,2 alkyl shift. So These mechanisms are the only ones that are going to show our carbocation rearrangements. Okay, so reaction one, we've already done a lot with it, so we'll just briefly remind ourselves. We have a starting material that looks like this, and so we treat it with some form of halogen acid like HCl or HBr or HI. We know that the first step will be what? It's going to be protonation, and so we start our arrows where? Electrons, and so we protonate like we've been doing all along. So in doing so, we end up with this carbocation, right? Because we want to undergo a Markovnikov addition, and so a Markovnikov addition would be where our hydrogen is going to add to this other hydrogen down here. So now we have a CH2, leaving our tertiary carbocation, which is more stable. So this is Markovnikov. And then what we have is we have our X floating along, and we're going to snap those together. Now, let's think about this. Our carbocation is planar, and so could we have approach for both the front face and the back face? Yeah, sure, they're equally likely, and so what we can do is we show that arrow, we'd show one of the products, and so let's draw the product where the X's come in on the front face. All right, so that product will push the methyl to the back, and so now we have our X there on the front face. Now, is that the only product that will form? Or we've also got the other product, which results from the addition of the X from the back face. And so in that case, the X wouldn't be on a wedge, it would be on a dash. You don't always have to draw both of those products. What you can also do is you could say, all right, Professor Walk, we do this reaction, we're going to end up with this product, and then we're also going to end up with it's an enantiomer. And so you could just say plus enantiomer, and I know exactly what you're talking about. I know that you're talking about a molecule with this exact connectivity, except now the X and the methyl group are swapped. So that's going to save you a little bit of time. On an exam, if I ask you to predict product, if you say plus enantiomer or plus diastereomer, that's perfectly fine. I've got you. All right, so the way we're going to do this is I don't know how many reactions we're going to get to before the exam. It could be 8 or 9, it could be 13. It depends on time, really. And so the way that we're going to easily categorize these, because I've kept talking a lot about how there's 3 main types of mechanisms, and so that is true. And so what we're going to do is we're going to put everything down on a table. And so I would strongly advise you to start a new page somewhere in your notebook. And so we're just going to pretty much list every reaction as we go. And so we're going to compare and contrast basically those reactions as we go. And it'll give you basically a one-stop shop to check out any of the electrophilic conditions that we do. If you write big, you might want to make save 2 pages. Yeah, you know how big you're writing. Okay, so the categories for our table will be as follows. All right, so the first thing we'll do is we'll just say that we have a reaction number. And so what that's going to do is that's going to allow you to go back in your notebook and say, oh, this is reaction number 1, so he's talking about this reaction right here. So this gives us a point of reference in our notebooks. The next thing we'll do is we'll talk about the electrophile and the nucleophile that end up on the molecule. And so what this does is it basically allows us to see, well, here we're adding an H and an X to our molecule, and over here we end up having added an H and an X. And so for this reaction number 1, we can say, well, what we've done for reaction 1 is we've added an H as the electrophile, and that was our first protonation step. And then our nucleophile that came in and attached later, we'll just say that's going to be an X. It's going to be some sort of halogen, right? All right, so the next thing we'll talk about will be the actual reagents that you'll see used. And we've seen everything thus far in here. So for an HX reaction, it's going to be a strong acid. So we could use HCl, HBr, or HI. Those are all perfectly valid. And so let's get those down on paper. HCl, HBr, and HI. Very ugly H. All right, so we'll talk about a couple of other things. We'll talk about regioselectivity. And we will talk about stereoselectivity. Can't talk about one without the other. Okay, so finally we'll end up with our reaction type, or our reaction class. So, for our type 1 mechanism, we've already used it once today. When we talk about the regioselectivity of a carbocation mechanism, what do we call it? Starts with an M. Markovnikov, right? So every time we do this reaction, we're going to go through the Markovnikov regioselectivity. And so what that ultimately means is that in the vast majority of cases, we're going to add our electrophile, our proton, the carbon with the most hydrogens already there, and by doing so, we form the more stable carbocation, and that's our favorite product. Of course, that can be, it can end up a little backwards sometimes because if there's resonance, that's going to dominate which is the more stable carbocation, but without resonance, it's always going to be Markov. All right, so then for stereoselectivity, does a carbocation mechanism have any stereoselectivity? It doesn't, right? And that's why it's so messy. And so unfortunately, for a C+ reaction type or a reaction mechanism, there's no stereoselectivity. So that's why there's lots of different options for products and why no one really does this chemistry in the lab. And so finally, the reaction type, that's just our mechanism, and we'll say it's C+, right? We know the mechanism that it goes through. It's going to go through a carbocation intermediate. All right, so as we go through these reactions, I'm going to be essentially making table listings, and so when we do so, you can add that to your table, and you'll end up with one page of all the reactions that we talked about. Okay, so let's go forward. Let's talk about reaction number 2. Reaction number 2, we are going to refer to as a hydration reaction, and specifically we'll say it is an acid CAT period. What is CAT period? What's a chemistry word that probably is? Catalyzed. It's an acid catalyzed reaction. All right, so hydration. What do you think of when you hear the word hydration? Water. All right. Okay, so essentially what we're going to do when we do an acid-catalyzed hydration reaction is we're going to add water to our alkene. That's the ultimate process that we're undergoing. So let's just show an example and see what this looks like. All right, so here we have this starting material right here. So we're going to have a couple of reactants. So first off, we're going to do a hydration reaction. We're going to have H2O. And so specifically, we're going to have lots of H2O, right? We might be just doing this reaction in water. It might be our solvent. We're going to have way more water than anything else in the reaction. In addition to the water in our starting alkene, we're also going to have catalytic HA, so catalytic acid of some kind. And so if it's catalytic, are we going to have a lot of it or are we going to have a little bit? What does catalytic mean? Basically, a catalyst is going to lower the activation energy for a reaction. So we don't need a lot of it. We need just a little bit of that catalytic acid. So anytime we say we've got catalytic acid, we would say that we have just a little bit. It's not necessary to add a full equivalent of acid as we have the alkene. We could have, this number could be as low as, let's see, regularly, you'll see a catalytic amount to be about 5%. People have developed really, really efficient catalysts that can be as low as like 0.01%. And so if your catalyst is a really, really expensive transition metal that you've spent, hundreds of thousands of dollars making, and you only end up with a little bit, well, that's okay because you only need a little bit in the first place. So that kind of can go into the pricing and things of catalysts. But our catalyst here is really cheap. It's just something like HCl, and that is definitely not costly. So let's think about what happens whenever we add a strong acid to water. So let's see, we've got H2O and we've got HX. And so a strong acid does what in water? Fully dissociates. And so if it fully dissociates, what we're going to end up with is some H3O plus, and we're going to end up with some X minus. And so our X minus doesn't really have much of a role in this reaction once we've added our catalyst, and we'll see why that isn't a reason. Okay, so we add a little bit of acid, we have a lot of water, and so all of our acid is converted into basically H3O plus and X minus. So once we add our acid and our water together, do we have any HX left? We don't, right? So the first thing it does is it's going to fully dissociate with that water. And so really what we've got to react with our alkene is going to be hydronium. Right here. Okay, so hydronium, what is a very common reactivity of hydronium? It acts as an acid, right? It has a pKa of around -1.7, so it's very acidic. And so based on everything we know about carbocation mechanisms, we have an alkene, we have a strong acid, what's going to happen? What happens when we have HCl as a strong acid with an alkene? What's the first step? Protonation. And so it's going to be the same thing here. We're going to have protonation of our alkene from our H3O+. And so we start our arrow at the alkene. We deprotonate that hydronium. So in doing so, we're going to form what kind of intermediate? What kind of intermediate do we always form with these acid-catalyzed reactions? Carbocation. So, which carbon are we going to add our proton to, the tertiary or the secondary? Again, we're going to follow Markovnikov's rule, which says we want to add to the carbon that will give us the more stable carbocation, or the carbon which is going to have the most protons there already. And so this has how many protons? None. This one has how many? 1. And so we're going to add to that bottom carbon. So what we end up with, all right, so wait, that's not right. All right, so we've got 1 there. And so what we end up with over here is going to be this tertiary carbocation. It's more stable. All right, so let's think about what we've got in solution. I guess we have a little bit of X minus. Yeah?
How did that H3O what we just did there?
So that's just an acid-base reaction, right? So we've got this acting as an acid, which we know is a proton donor or an electron acceptor. And then we've got this acting as a base, which is a proton acceptor and an electron donor, right? So it is accepting its electrons to this proton, so basically you can grab it and deprotonate the water. Yeah, so it's the same process as if we had treated this with something like HX, except now our HX is H3O+. That's our source of protons now. All right, so what have we got in solution? I guess we've got a little bit of X minus floating around, so we'll say that's just a little. And then we've still got a ton of water. We've got lots and lots and lots of water. So we've still got lots here. All right, so these things, of course, have electrons on them. So the X is going to have 4 lone pairs, and the oxygen is going to have 2 lone pairs. All right, so which do you think is going to snap to that carbocation? Is it going to be the negatively charged X minus, or is it going to be the water? Initially, you might think it's the X minus, right? It's negatively charged. Well, let's think about something. We've only got the HX, or the HA. All right, sorry. Let's change this to HX. All right, so we've only got our HX there, a little bit of amount. So how much X minus can we form from just a little bit of HX? Just a little bit, and so if we get 5% of HX, we can only ever actually add about 5% of the product, or we would only end up with 5% of the product resulting from the addition there. So first off, there's 2 important things. First off, there is lots more H2O than X minus. And then furthermore, what we can say about water versus X minus is that H2O is much more nucleophilic. And so not only is there much more water there to react with our carbocation, it is also more reactive with the carbocation. And so with those 2 things both pointing towards the addition of the water to our carbocation, that's exactly what we see. So when we snap together our water with our carbocation, where do we start our arrow? Electrons. What electrons? On the water. And so we start right there. We snap to our carbocation. All right, so what does that look like? So our carbocation is sp2 hybridized, and so it's a trigonal planar molecule, and so we can attack our carbocation from both the front face as well as the back face. So if we attack the carbocation with our water from the front face, will we end up with our water on a wedge or on a dash? That should be on a wedge if it comes from the front. And so our methyl is going to be pushed where? Yeah, it's going to be pushed back, and so now our methyl is going to be on a dash. So nothing else has changed about that oxygen. It's still got 2 protons connected to it. All right, so when we draw this structure, in this picture, we have a positive charge on the carbon. Should we still have that carbocation? No, that's gone away. Basically, we filled that open shell of the carbocation with electrons from the water. Where does essentially the positive charge move to? Now it's on the oxygen, and so now what we've got is a positive charge there. And so importantly, we never want to end up with a product that is charged. We always want to end up with a neutral product. So let's write that. We always want a neutral product. And so what that means is we're going to have to go through one more step. Essentially, this is going to be one more acid-base reaction. So all along, what have I been saying that we have a lot of in this reaction? Water. We have lots of water in this reaction. So what we can do is if we have water just floating around, which we almost certainly do because there's lots and lots and lots of it, what we can do is now we can donate electrons from this water to undergo one more acid-base reaction. And so what we'd end up with in this case would be this product. So is this going to be a charged product or a neutral product? This is now a neutral product. What functional group have we essentially added to our double bond? Yeah, that's an alcohol. And so a hydration reaction is a way that essentially we can use catalytic acid with water and we can end up with a new alcohol. It's a way to make alcohols. All right, let's think about the stereochemistry here. So I said that we could attack this carbocation by the water from the front face, but of course we could also attack from the back face. And instead of drawing that, what we could say is we could just say, well, we're going to form this intermediate plus it's an enantiomer. And so if we're going to have that intermediate, when we finally get down to our product, we'll not only just have this product, but we'll have this product plus it's an enantiomer. All right, so we're really going to be able to form two products in this case, but we don't always have to draw them all out. What product have we not listed here? All right, so we undergo an acid-base reaction, right? And the water acts as a base. And so what is it going to end up as down here? Yeah, we're going to end up as hydronium. And so the question we can ask ourselves, or really I guess answer now, is why do we only need a catalytic amount of acid in this reaction? So we have hydronium here that kickstarts the reaction. That's our acid to get this thing going. What do we end up with down here? Hydronium. And so basically we start with hydronium, it starts our reaction, and it also ends up as a product. And so now this hydronium is free to go all the way back up here and essentially kickstart this thing again. So if we only have a little bit of acid, that's okay, because every time we go through this mechanism, we're going to regenerate our acid, and so we can have basically all of the reaction take place. So we have our acid, and it is regenerated. Allows us to use just a little bit of that H-axis. We only need a little bit of the hydronium to start out with. All right, so this mechanism is slightly different. It still goes through a carbocation, but now how many intermediates do we have from starting material to product? We have two. All right, so let's think about the stability of those intermediates. So we've got a carbocation intermediate, and then we've got an oxygen with a positive charge that's an intermediate. So which do you think is more stable, a C plus or an O plus? What's rule number one in thinking about stability of intermediates? Full shell, open shell, right? We want to think about whether these things are open shell or closed shell. Which is a closed shell intermediate, this one or this one? Which is definitely open shell? The carbocation, right? Here, this oxygen, does it have a satisfied octet? Yeah, it's got a closed shell. And so since the carbocation is open shell and the O plus is closed shell, which is more stable? Definitely the O plus. So if we're to draw an energy diagram, it would look something like this. All right, so we've got energy, we've got reaction, progression. And so we have our starting material and our products, and we don't ever really care too much about their energy levels. But we need to show our two intermediates. And so going from left to right, do we hit our carbocation first, or do we hit our O plus first? We hit our carbocation first. And then furthermore, which do we want to have higher in energy, the C plus or the O plus? We want the C plus, right? Because it's less stable. It's open shell. And so that's exactly what we show. We have a C plus here, and then lower in energy, further on down the road, we would have an O plus. All right, so we can imagine our path to starting in our starting material and going to product. So we would start here, we get into this hill and then down the hill, and so we end up as our carbocation. Then we'd have a small hill to climb to go to O+, and then we'd have another small hill to climb to go to our product. And so when we think about the rate determining step of this reaction, even though we now have multiple steps, is the rate determining step still the formation of that carbocation? What's the highest energy, basically, transition state? It's this one right here. And so just like in the previous reactions where you've only had one intermediate, even though we have two intermediates, we've still got a rate determining step that is the formation of the carbocation. So that's why this reaction we pretty much just consider to be a C+ reaction. The O+ part, it's downhill. That's going to be a really fast part of the reaction. The first part, the formation of that carbocation, is still the rate determining step. All right, so let's fill in our table for that. So this will be reaction number 2. And so our electrophile in this case, what do we end up with on our product as the electrophile? It's the same thing as the previous one, right? It's just an H. We've added an H as our electrophile. And so what we're going to find is anytime we have a carbocation mechanism, that electrophile will be an H. And so alternatively, now we have a new nucleophile. So in reaction number 1, we ended up with a chlorine or a bromine or an iodine on our product. What do we end up with on our product as the nucleophile now? We end up with that product. And so basically the way that I like to write this is it's going to be a quick guide. So what do you end up with? What are the new bonds that we've formed? So in this case, what we've added to our double bond, or our alkene, is we've added a hydrogen, and now we've added an OH, right? That's the end product that we have. All right, so for reagents, what are we always going to have in this reaction to do a hydration? Yeah, we've got to have water. So we always have water. And so in addition to the water, what we want is a catalytic amount of acid. And so typically you'll see any of the halogen acids like HCl, HBr, HI. Have you ever seen HF? No, it's not a strong acid, so it can't be HF. And then furthermore, what you might see is sulfuric acid, so that'll be used quite a bit in these reactions. Really, any strong acid that can jumpstart a reaction is going to be acceptable, but we only want it there in catalytic amounts. All right, so the regiochemistry here, would you describe it as Markovnikov or anything else? Yeah, are we adding our electrophile to the carbon with the most hydrogens? Yeah, and so in this case, anytime we have a carbocation mechanism, it's going to be Markovnikov. We're going to find that our last category, where we have our reaction type, we're going to end up, anything that's the same reaction type is going to end up having almost always the same regiochemistry and the same stereochemistry. All right, so stereoselectivity of this reaction. Is it good? Are we going to end up with a lot of products, or are we just going to end up with a few? We'd end up with a lot, right? Because again, we're going through the protonation step, and so our alkene can either be protonated from the top face or the bottom face, and then our second step is the snapping together of our water to the carbocation, and so that's again planar, and so the water can come from the top or the bottom, and so there's a lot of different possibilities. And so again, big time weakness of these carbocation mechanisms is that there's no stereoselectivity. All right, so then for reaction type, we'll just call that C+. All right, so it's the same thing as reaction number 1. Okay. We're going to skip ahead a little bit. There is a third reaction I had initially planned talking about. If we have time next Friday, it's a very close derivative to this, so I don't want to spend time on it right now. But if we have time, we might come back to it and look at it briefly. So we're going to skip ahead now to something. Roman numeral number 5. So we're going to start in mechanism type 2. So we've done mechanism type 1. That's our carbocation mechanisms. And so at least by the end of class, we want to have an idea of what these type 2 mechanisms are. So we'll call this thing mechanism type 2. And so our nickname for this, what we're going to do is we're going to call them polonium reactions. And so we'll symbolize that. We can symbolize it in two ways. We could just call it an X plus, or you might see it written as this little three-membered ring, which has an X plus in it. All right, so those are going to be halonium mechanisms. So that's how we'll abbreviate it. All right, so let's start with the same starting material, and let's talk about how these things work. This is going to be a lot faster than talking about the carbocation mechanism because there's better control. All right, so we'll start with our trusty starting material here, and we will react with an electrophile and a nucleophile. Now let's think about the charge buildup that we might have on an electrophile and nucleophile. So if we have an electrophile, something that's going to react with electron density, would you expect that to be partially positive or partially negative? It should be partially positive, right, if it's attracted to electrons, and so that's exactly what we've got. So we're going to have a partial positive charge there, which means we're going to have a slight partial negative charge on our nucleophile. All right, so knowing what we know about carbocation mechanisms, how do you think we start this? Yeah, and so we're not going to protonate here because we're never going to find the protons or what are the electrophiles, and specifically, what we're going to find is the electrophile in these mechanisms always have to have a lone pair, and since protons can't have a lone pair, protons aren't going to qualify for these halonium mechanisms. And so always, we say the electrophile has to have a lone pair. So everything up to this point is going to be the same. So we're going to start our arrow at our alkene like we've been doing all along, and we're going to draw it to our electrophile. And so what's going to happen to the bond between the electrophile and the nucleophile? What's it been doing all along? It's been breaking, and so it's still going to break. Everything's the same. There's going to be one arrow on this mechanism that looks a little bit different. All right? And so with our carbocation mechanisms, what we've always been talking about is we're going to attach our electrophile to one of the carbons, leaving the other one open shell and electron deficient. That's our carbocation, right? In this case, we're not going to do that. So we've got these red electrons on our electrophile, and instead of attaching our electrophile just to our secondary carbon, the electrons from the electrophile are going to go ahead and attach themselves to the tertiary carbon. All right, so what does this look like? What we end up with is essentially we're going to have our electrophile bonded to both the top carbon as well as the bottom carbon. And that's why we talk about this as a halonium mechanism. It's because we're going to form a three-membered ring with our halogen, or with what we'll find to be a halogen. In this case, we're just calling it an E, a three-membered ring with a positive charge. And so let's think about what this would be like. So if we're going to attach our electrophile to both of these carbons at the same time, what we're going to have to do is approach from either the front face or the back face. But we're never going to be able to approach it such that the electrophile would be a wedge on one of the carbons or a dash on the other carbon. So what that means is for our planar alkene, we're either going to approach from the front face, and so we have our electrophile on a wedge here with a plus charge, or we would have our electrophile on a dash, which would require that to be on a wedge. All right, so that's our two options. What's the relationship between these two things? Yeah, they're enantiomers. Both chiral centers are flipped, and so what we've got is a pair of enantiomers. All right, so this is our halonium intermediate, and this is why we call these things the X plus mechanism, because in most cases, the electrophile is going to be a halogen, which we can simplify it as X. Hello.
Hello, the FBI reports there is a home break-in every 15 seconds.
So now you know. Something makes me think that was not the FBI. Okay, I lost my train of thought. Okay, so we've got our halonium intermediates. That's what we call this, the halonium mechanisms, and so that's where we're at. So we've still got our nucleophile that's gone on its walkabout. It's just been out in the reaction. And so finally it sees that we have a positively charged intermediate. And so what we're going to do is, just like in our carbocation mechanisms, we're going to snap charges together. So we've got a negatively charged nucleophile, positively charged halonium. Okay, so do you think we're ever going to add our nucleophile to the electrophile? Would that be an electrophilic addition? I've said that in an electrophilic addition, we always want to add an electrophile to one carbon and a nucleophile to the other. And so that's what we're always going to do. So in this case, we want to add our nucleophile to one of those carbons, which leads us to a really important question. Which carbon is it going to add to, the top one or the bottom one? Yeah, 10 o'clock was pretty much split, and I'm guessing you guys are going to be too. And so what we have to do is we have to think a little more in depth about what's really going on. So let's talk about that. All right, so let's label this little area as regiochem. And so what we've got when we talk about the regiochemistry of this reaction is, let's draw our intermediate out again. And so I'm not going to worry about stereochemistry. I'm drawing that in here. That's just extra information we don't care about right now. So what we've got is an intermediate that looks like this. Okay, that's our intermediate. So what we want to do is we want to think about, what could this be in equilibrium with, right? Things are often in equilibrium with other species, and so in this case, that's exactly what we find. And so we've got a positively charged electrophile. What we can find is that they're actually in equilibrium with some carbocations. Now, the carbocations do not make a very strong, words are escaping me. They don't contribute much to the overall nature of this structure, but they do contribute a little bit. And so, let's see, we could take this bond, start at the electrons, and just put those as a lone pair on the electrophile. All right, so if we do so, we're going to end up with a structure that looks like this. And so now we're going to have a carbocation there. What kind of carbocation is that? Secondary. So it doesn't make much of a contribution, but it makes a little bit of a contribution. Likewise, we could also break the other bond, and let's see what that would look like. So if we break this bond, we'll still end up with a carbocation, but now we're going to end up with a carbocation there. And so what kind of carbocation is that? That is a tertiary carbocation. All right, so let's think about the biggest contributors. First and foremost, what is the biggest contribution here? And remember, we're not talking resonance structures now. We're showing equilibrium arrows, and so these things actually exist just a little bit as their own thing, right? So what is the most stable structure that I've drawn of these three? What's rule number one? Closed shell, open shell. Which of these is closed shell? It's the middle one, right? Because the other two have carbocations. It's the middle one that has basically satisfied these carbocations. And so what we've got is the most stable here. And so that's why we draw the halonium intermediate, because 99.99% of this thing is just right like this. It is as the halonium intermediate. But there is the slightest contribution that these other structures make. And so between the red structure and the blue structure, which do you think makes more of a contribution? Why blue? It's tertiary, right? We know that based on the rules we've already learned when we talk about carbocation stability. And so this is going to be the least stable. Why I would write that in blue, I don't know. Least stable. So I guess this one is, blue one is middle stable. The important thing is that the blue one is going to make more of a contribution than the red one. And so if we go back up to our intermediate right here, and we were to assign partial charges, what we could say is that there's going to be a partial positive charge on that tertiary intermediate, or on that tertiary carbon. And the reason is that when we go down here, we see that, well, it's because this structure right here makes more of a contribution than this structure. And so if this makes more of a contribution, this carbon right here is going to be a little more positively charged than the bottom carbon right here. All right, so we've got a partial positive charge on that top carbon compared to the bottom carbon. And so now, when we snap together our nucleophile to our halonium intermediate, which carbon do you think it's going to add to? Which one has more positive charge, top or bottom? Top. It's definitely going to go right to that top carbon. Okay, so our nucleophile in both cases we'll add in to our top carbon. All right, and so in the process, what happens is essentially this bond between the electrophile and the carbon, it pops open. All right, so it pops open. So now we need to think about, all right, stereochemically, what is going on in this picture? And so, all right, so let's write a little section. It says stereochem. And so this phrase has been on so many chemistry club t-shirts, I'm sure, over the decades at lots of different universities. What you want to remember is that anytime we do a displacement, so we'll say a displacement. And so in this case, a displacement is basically saying that we're going to take our nucleophile, we're going to come in and form a new bond, and we're displacing our electrophile, right? The nucleophile is forcing the electrophile away. A displacement requires what we can easily remember as a backside attack. All right, so if you remember a backside attack, anytime we undergo a displacement reaction, you're going to be able to remember what the orientation of the incoming nucleophile will be. So, thinking about it this way, if our nucleophile is coming into this top structure, and the electrophile is on the front face, and we have to do a backside attack, meaning that we approach basically the opposite side as our electrophile, is our nucleophile going to attack from the front or the back? It's going to attack from the back. And so in the product, is that going to end up the nucleophile on a wedge or a dash? If it attacks from the back. Dash, right? A dash indicates is going towards the back of the board. And so, when we draw our product, we'll have our nucleophile on a dash. Our methyl group, which was on a dash, is now, what's happened to it? It's been pushed to the front, and so now our methyl group is going to be a wedge. And then the bond between the electrophile and the bottom carbon, have we done any chemistry there? Nothing changed, and so is it going to be on a wedge or a dash? It was on a wedge, and it's still on a wedge. We didn't do anything. All right, so our electrophile is still in the front. And then alternatively, with the bottom halonium intermediate, we have our nucleophile coming in and displacing our electrophile. Now our electrophile is on a dash, and it's in the back. And so if our nucleophile needs to come in and do a backside attack, is it going to approach from the front or the back? This case, it's going to come in from the front because that is the backside of our electrophile that is on a dash. And so when we draw our product, will our nucleophile on the bottom, on this bottom structure, will it be on a wedge or a dash? Yeah, it'll now be on a wedge. Our methyl group, for the same reasoning as above, will be pushed backwards. Now it's on a dash. And so the electrophile on the bottom, will this be here on a wedge or a dash? We didn't do any chemistry there in this step, and so it stays how it was. It's going to be on a dash. All right, so we should recognize a relationship between the nucleophile and the electrophile addition in both cases. We talked about there can be syn addition or anti-addition, and so in the case of these halonium mechanisms, are we going to have stereoselectivity? Yeah, and so is it going to be syn or anti? It's going to be anti. You can see in both cases we've got the anti-product where the nucleophile and the electrophile are on opposite faces. So, with a type 2 mechanism, we're always going to see anti-stereochemistry. For regiochemistry, would you describe that? Would we describe it as Markovnikov or anti-Markovnikov? Do we end up with our nucleophile attacking the more substituted carbon? Yeah, just like we did with the carbocation mechanisms, and so we'll also describe this as Markovnikov. And let me go ahead and add, when we're talking about regiochemistry, we're only going to learn one reaction that doesn't essentially have Markovnikov regioselectivity. So we'll see one case, not in a type 1 or type 2 mechanism. We'll save that for type 3. We'll see one case where we see an anti-Markovnikov regioselective reaction. Okay, I will be out of town. I'll respond to a few emails, but otherwise I won't be very responsive. Otherwise, have a great weekend. Office hours today, 12:30 to 1:30.